So what are the equations of motion in fluid mechanics? So we'll try to derive solution for some few fluid mechanics problems, some simple problems. So first we write the equations of motion. You know that rho dv by dt is equal to the net force on the particle. So your net force on the material particle. So you have a material particle of infinitesimal volume. So you call it material particle. The mass of the particle is rho into its volume. So this force is also per unit volume. All these terms are per unit volume. So what is the net force? Net force is because of the stress gradient, or you call it divergence of stress, plus some body force. So there may be an external body force like gravitational force. So this is the one equation which is written for the particle. So index I is the free index here in each term. So this is a force balance in I direction. Now this, we had told you that this can be written as del V by del T plus gradient of V into V. So because this is an Eulerian form, Eulerian description, so you can write this velocity, this acceleration as this. There is a local derivative, there is a convective term. Now we replace sigma with minus P plus, so this is where we represent your stress in fluid mechanics. Sum of mean stress plus viscous stress. So now we have to do this operation, divergence of this. So what we got, I had already told you, minus gradient of P plus, no, minus gradient of P. If you expand your shear stress as in terms of strain rates using the constitutive equation of viscous fluids, you can replace this tau ij comma j with eta del square u plus, so you can replace this term with these terms. So you have used the constitutive equation for fluids. So eta is the coefficient of viscosity. Instead of mu, I am preferring eta because your mu looks like velocity. Now, any problem with this? This equation we have already done. So if I want to write the equation in expanded form, so it was dv by dt. Now, this dv by dt you can write as, suppose you say your v is v1, v2, v3. So your first equation becomes rho dv1 by dt is equal to minus del P by del X plus eta. Assume incompressible flow. So this term goes to zero for incompressible flow. We already told the divergence of velocity is zero for an incompressible flow. So your equations are simplified. Any questions?
No, sir.
So this is your first equation. So what is your second equation? If you have got okay, if you have a gravitational force, so you will have to add minus rho g. Suppose you have a gravitational force in y direction, it is downwards, so you have to write minus rho g. And your third equation is, so I have written all the three equations. So these are not
Ex-
called, also called Navier-Stokes equations.
Excuse me, sir.
Yeah,
So in the second equation, sir, like the last term, sir, D2, sir, is it V3 or V2? Like del square.
okay. So, so it is del square V. So you have pointed it correctly.
Yes, sir.
So del square V means basically Laplacian of vector V. So you are having an operator. So this applies to vector V. So it is like a, so it is a summation. This summation applies to vector V. So you will get three terms. This has to for V1. Similarly for V2, then V3. Okay. So you are getting a vector. Your output is a vector. This is also written as this. So now let's do a simple problem. So you take a plate and you have another plate which is moving forward with some velocity v10, and you have a fluid here. So this is a fixed plate. Now what is there? Top plate is moving with v10. So what you say is that this velocity v1 is a function of y, and you take a coordinate system. Can you say that velocity v1 is a function of y? It doesn't depend on x. You see it is 0 here, your velocity, maximum here, in between it is varying. But we say that this same thing is everywhere. You see, top plate is moving with the velocity v1.
Excuse me,
So
sir.
you, yeah,
Sir, if the plate is movable, then it will have x also, no?
so plate is moving rigidly.
Okay.
So velocity is in x direction x,
Yes, sir.
but it is a function of only y. Any problem?
No, sir.
No, sir.
No, sir.
Okay. Same thing will happen to all other quantities. For example, pressure. It will be also a function of y. Nothing is changing in x direction. You see, everywhere you have same situation. Also, these all other components of velocity are zero. Okay, so now we write equation of motion. So if you have got such a situation, what is the acceleration? Suppose you take any particle, acceleration is given by, suppose I del v by del t plus gradient of v into v. So this was my acceleration term. Now we are assuming a steady flow. So steady flow means derivative with time is zero. This term goes to zero. Now you have gradient of v into v. So what is gradient of this? What is the velocity v here? v1 0 0. So you don't have v2 and v3. Now if you look at del v1 by del x, you have got vi comma j del v1 by del x. v1 is a function of y. So del v1 by del x is 0. Del v1 by del y, okay, v1 comma z is 0. v2, v3 are all 0, so they will be 0. Any problem with this? So what do you see after product? So there is no acceleration. None of the particles is accelerating. Do you have any problem with this?
No, sir.
No, sir.
Okay. You see, you have a gradient only in y direction, but your particles are moving in x direction. So no particle from here can go to here. Only then it can accelerate because change in velocity is only in this direction.
Yes,
If
sir.
this fellow keeps going like this, its velocity will never change. So your acceleration terms are zero. So we write the first equation. Your acceleration term is zero, so this becomes this minus del p by del x plus eta del square v1 by del x square. Any problem with this equation? Now in this equation, you see v1 is only a function of y. So these terms go to zero. So what do you get? All
Sir,
right. Yeah.
why dv by dt is zero? Just that part.
Why? What is zero?
Sir, dv by dt is zero. Like for this acceleration is zero in the
Yeah,
left hand
dv
side.
by dt is zero. I just showed you. Gradient of v into v. You see, all these particles are going in a straight line. So, and you see, velocity is not a function of x. So they will never accelerate. If you look at a particle, follow the motion of a particle. A particle will accelerate only if it had gone vertically upwards, because there is only velocity gradient. And since it is not allowed to go vertically upward, so this motion is not there. Only there is horizontal motion. I told you physically why acceleration is zero of a particle. Okay. Now in this term, these two are zero. Only this one is non-zero. So you have written it. Now you look at the second equation. 0 minus del p by del y plus eta. You see, they were second velocity in y direction. Since there is no velocity in y direction, so all these terms are zero, implies del p by del y is equal to zero. This implies p is equal to constant. Already you knew that p is only a function of y. Del p by del x is already zero. So this is also zero. Any problem with this? Similarly, you will see already the third equation will also give you nothing. So p is not a function of z also. P was only expected to be a function of y. So we have neglected gravitational force. Okay. Otherwise, you will get some variation with y. So now what is your equation? D square v1 by dy square is equal to 0. So this is the differential equation you have now to solve. And what are your boundary conditions? This is moving with v1 0. This is fixed. Now you integrate it. So dv1 by dy is equal to some constant a. Further integration will give v1 is equal to ay plus b. Now you have got two constants. You use the boundary conditions. So at y is equal to 0, this is y is equal to 0. This is y is equal to h. So you put y is equal to 0, velocity is 0. So b becomes 0. At y is equal to h, velocity is v1 0. It means a is equal to v1 0 by h. So what is the velocity? So this is a velocity distribution. So you see velocity, how does the velocity vary? So this is the velocity distribution between the plates. This is your y is equal to h. This is your velocity v1 0. If you put y is equal to h, you get v1 0. Any problem with this?
No, sir.
So it was a very simple situation. Pressure is constant everywhere, and your velocity increases linearly. So what are your shear stresses? So what was the expression for shear stresses? So we are neglected. We are saying fluid is incompressible, so other term is not there. So that's all we have for viscous stresses. Now you have got this. This is a coordinate system, x and y. So what is a tau xy? 2 eta del u by del y. Okay, let's call it. The strain rate is given by this expression. If we are wanting tau xy is here in this case tau 12. The nomenclature I have used. So what do you get? Eta. And what is your V is equal to? So what is your del V1 by del Y? So eta into any problem? This term is 0. So I'm mixing Y and X1, X2. So you understand what is happening. So this is a shear stress. Now look at this value of shear stress. Is it a function of Y?
No, sir.
No, sir.
So it is turning out to be constant. So this was your fluid. So this was top surface was moving with V1 0. Now if you look at shear stress, if I take an element here, shear stress is positive. So how you represent positive shear stress? Like this. If you take a small element here, sorry, shear stress has to be like this because this is the negative y direction. So force has to be negative. Can you see this? And if you take an element at this position, I mean here, then okay. Let's take it here itself. So what is happening at this surface? Positive shear stress mean this is the direction. This is the top surface of the fluid. This is the bottom surface of the fluid. The bottom surface of the fluid, the force has to be like this for it the shear stress to be positive. Can you see this? So if you take the plate, this is a plate. So what is the force on the plate? This is the force on the fluid. The force on the plate will be like this, equal and opposite. Similarly, this surface, So this was a plate. Now force on the plate will be, can you see this? So you see bottom surface was being pulled in the forward direction, while top surface is suffering drag in the reverse direction. And this also is, you see, physically appealing. It is moving forward. So fluid has to apply resistance to it, and that force has to be in this direction. Similarly here, fluid is flowing in this direction. It will try to drag the plate along in this direction. So force on plate. And due to pressure, you have only a normal force on both the plates. Any problem? If you have any questions, please ask. Bhava, is it all right?
Yes, sir.
Okay. So can you find mean velocity at the cross section? You see, your velocity is, this was a velocity distribution. So if you want average velocity, you have to do an integration of this kind. So what do you get? V10 by h.
Sir, it is coming around 2u by 3.
Even
Up.
h by 2.
Do you see any problem in what I have done?
No, sir.
Okay, let's move further. So we do another problem. We take two plates. Now both plates are fixed and flow is happening due to a pressure gradient. So you have got some delta P by delta X in X direction. So what is the pressure gradient? You can say, suppose you have the length of these plates is L, and you have a higher pressure here. So this delta P is, so delta P is P1 minus P2. So pressure is higher here, lower here. So that is why you are having a negative sign. Because what will be the pressure gradient? This pressure minus this pressure upon length. So that is why you get delta P by delta X is this. So for this pressure gradient, you have to find the velocity of the fluid. Okay. Again, you are having flow in only X direction. So you have got only V1. V2, V3 are 0. Okay. Now again, you see velocity will depend on Y. It is 0 here. Flow is occurring. So there has to be some variation in Y direction. So we can say V1 is a function of Y only. So we'll see what is if something else is there. So let's write the equation in X direction. So again, you will find that your acceleration is 0 in X direction because the flow is occurring only in this direction.
Sir, can you please scroll up? Just I want to see one
Yeah.
minute. Can you please scroll up? Like,
Are you hearing me?
yes, sir.
Okay. So you see, I am writing force balance in X direction. So minus del P by del X plus eta del square V1 by del Y square. There is no variation in X and Z direction. Your velocity is only varying in Y direction. Okay, we'll see further. In what is the equation of motion in Y direction? Now there is no velocity in Y direction. So these terms are 0. So this implies del P by del Y is equal to 0. So P is only a function of X. Similarly, third equation will give you del P by del Z is 0. So your P is only a function of X. So if you write your first equation, all right, you can write your first equation as this. Now this is only a function of X. Okay. Now what about this? We said that V1 is only a function of Y. So the left hand side is only a function of Y. So left hand side is a function of right hand side is a function of x. So what does it mean? It has to be equal to a constant.
Yes.
So dp by dx is equal to a constant. So this is equal to any problem. So if you integrate, let's call it a. So this is a velocity distribution. Now you apply boundary conditions. This was a y is equal to 0, y is equal to h. So your velocity is 0. It implies this b is 0. What does it imply? So this implies a is equal to, so your v1 is equal to, so this is your velocity distribution. So what you find is, put y is equal to 0, you get a 0. Put y is equal to h, again you get a 0. You will find this is a parabolic distribution. This is a velocity. So velocity is maximum in the middle and it is 0 at the walls. If you want to find average velocity, so what you get, y cube by 3 minus hy square by 2. You have done an integration. And so you have to also divide by h. That is what we did not do in the last previous case. You see, for finding the average, you have to divide by h also. So your average velocity is v10 by 2. So you got an average velocity. So this is equal to, you have to put the limits 0 to h. So this is your average velocity. Any problem? You see dp by dx is negative. So, so you get a positive average velocity. You need pressure gradient to drive the fluid. So since we have got dv v1, so we can find dv1 by dy. What do we get? 2 eta dp by dx, 2y minus h. So this is your velocity gradient. What is your shear stress? Let's call it tau xy. It will be eta dv1 by dy. So you get 1 by 2 dp by dx, 2y minus h. So this is your shear stress. Any problem?
No, sir.
Okay. So we find tau xy at y is equal to 0. What do you get? You find tau xy at y is equal to h. Okay. So you have found shear stress both at the lower wall and the higher wall. So this is a fluid. You're finding the shear stress at the fluid. You see, this is negative. This is negative. So this term becomes positive. This term becomes negative. So positive shear stress here means what? If you take a fluid element here, it has to be like this because this is a negative y direction. So positive shear stress has to be in negative x direction. Do you understand all this?
Yes,
Otherwise,
yes.
I'll explain you. Similarly, this thing, this element is at the top surface. So you have a negative shear stress. So it means it has to be like this because area normal is positive, so force has to be negative for a negative stress. Now what happens to the wall? Newton's third law. This fluid is suffering a force in the opposite this direction, so wall has to get a force in this direction. Now here, this is a wall. Wall has to get a force in this direction. So you see, wall is getting a force in positive x direction. You have a fixed wall, fluid is flowing. There is a pressure gradient here, which is driving the flow. So wall has to be dragged along the fluid. So there has to be a force on the wall in positive x direction. Can you see this?
Yes, sir.
So I'll just explain you the sign convention of stresses because at times this can create a lot of problem.